Welcome back. So today we have the pleasure of starting chapter 12. Now, chapter 11 was an extension of the ideas of Calculus 1 from the single variable setting to the multivariable setting. And what we're going to be doing in chapter 12 is we're going to be extending the ideas of Calculus 2. And we're going to talk about how to do integration for functions of two variables, of three variables, instead of functions of one variable alone. And to begin with, we're going to talk about something called a double integral, which is an integral for a function of two variables. And we're going to interpret it as a net volume, and we're going to try and estimate the values of integrals using volumes of rectangular solids, sort of the 2D version of Riemann sums, which you did at the beginning of Calculus 2. Okay, so let's go ahead and get started. The setting is that you have some function f of xy, function of two variables, and you have some region, let's call it R, that has been scraped out of the xy plane, sort of as in this drawing here on the bottom left. We have the xy plane drawn below, and the region R, in this case, which is a rectangular region, has been indicated on the xy plane. And then we have some function, f of xy, whose graph is sort of hanging out either above or below that region. If we want to think about this quantity, this is called a double integral to reflect the fact that we have two variables, and corresponding to that we have two integral signs. This is not a typo. This is intentional, two integral symbols corresponding to a double integral. This quantity, the double integral over the region R of the function f of xy, represents the net volume under the graph of f of xy. To make sense of that, let's go back to Calculus 2 for a minute. Let's write a little thought bubble here. And let's remember that back in Calculus 2, you had some function, maybe it did something like this, going from a region, an interval from a to b in the xy plane, just in the x-axis this time. And if we considered the single integral from a to b of f of x dx, that represented the net area between this curve and the x-axis, called the net area because regions above the x-axis were counted as positive, whereas regions below the x-axis were counted as negative. The exact same thing is happening here. The single integral gave you the net area under the graph of a single variable function, whereas the double integral gives you the net volume under the graph of a two variable function. Regions above the xy plane are counted as positive, whereas regions below the xy plane are counted as negative. Volumes above xy plane are counted as positive. Volumes below the xy plane are counted as negative. And over the course of this chapter, we'll be developing a variety of different tips and tricks and techniques that we can use to actually calculate the value of these double integrals and actually calculate the size of this volume. But for today, all that we're going to do is we're going to try and estimate this volume. Similar to how you estimated net area using rectangles in a technique called Riemann sums. Riemann sums, which involved filling up the region between the graph and the x-axis with rectangles finding the area of each of those rectangles and adding those areas together to give you at least a decent estimate for the area between the graph and the x-axis. Not perfect, sometimes very bad, but at least it got you started. Now, rectangles are two-dimensional objects, and their three-dimensional equivalent is something called a rectangular solid. And so what we're going to do in the next example is indicated by this extremely blurry scanned image over here from your textbook. Here on the top, we have the graph of some surface f of xy. And then we'll try and fill up the region between that surface and the xy plane using a bunch of rectangular solids, rectangles that have a length, a width, and a height, so that they occupy 3 dimensions and have a volume. We're going to add up the volume of 4 different rectangular solids to get an extremely bad estimate of the volume under this graph. Okay, to make that more precise, let's read the entire problem. Someone describes to me a region R in the xy plane consisting of all the x's in the interval from 0 to 1 and all the y's in the interval from 0 to 1. And this kind of set, this kind of rectangular set, is going to come up pretty often. And we're going to call this set 0, 1 times 0, 1. X's cross the allowed y values. Let's estimate the value of the double integral over the region R of the function 2 minus x squared minus y. Now notice as well, this closing symbol on the far end of the double integral is neither an x nor a y, but rather we say dA. A stands for area to indicate the fact that this is a function of 2 variables, and so the base is going to consist of little areas, not little bits of x and y. Now it says estimate this value by adding up the volume of 4 rectangular solids. So just as in this image, we're going to add up the volume of 4 rectangular solids. And now they're going to tell us how to create these solids. To form the base, divide the region R into 4 equal squares. To form the height, use the value of the function at the upper right corner of the square base. All right, there's a lot going on in that paragraph. So let's just break it down a little bit at a time. Let's start by drawing the region R on the xy plane. It was the set of all points in the xy plane so that the x-axis was between 0 and 1 and the y-coordinate was between 0 and 1. And the points satisfying this restriction make up what's called the unit square. All the points in this square from 0 all the way up to 1 make up the region R. Now they say divide the region R into 4 equal squares, which I've done using these cyan lines here. And so I will call this base number 1, base number 2, base number 3, and base number 4. The 4 bases of the 4 rectangular solids whose volume we're going to find. Then it says, okay, so how high are your rectangles? To find the height, use the value of the function at the upper right corner of the square base. So we have upper right corner number 1, upper right corner number 2, upper right corner number 3, and upper right corner number 4. Upper right corner number 1 is located directly between 0 and 1 in both the x and y directions. So it has the coordinates 1/2, 1/2. upper right corner number 2 is located at the x equals 1 line, and the y has a value of 1/2. And the opposite is true for the upper right corner of box number 3. 1/2. Finally, this corner here of base number 4 has coordinates 1, 1, and it's the far end of the square here. Alright, so let's find the volume of these 4 rectangular solids by multiplying the area of the base by the height of the rectangular solid. Let's just jot that down. Volume of solid equals area of base times the height of the solid. All right, now let's consider first the area of these bases. These bases, every single one of them, is 1/2 a unit wide and 1/2 a unit tall. So the area of each base is equal to the width times the length is equal to 1/4 squared units. Now let's consider the height of each of these rectangular solids. They tell me to find the height of these rectangular solids, plug in their upper right corner to the function. The function's value at its upper right corner is going to be the height for these solids. So let's, for example, plug in the upper right corner of box number 1, which was 1/2, 1/2, into the function f of x, y. So height number 1, let's plug in corner number 1 into the function, and we get 2 minus 1/2 squared minus 1/2, which is equal to 2 take away 3/4, which is equal to, I suppose, 5/4. The height of box number 2, let's plug in the upper right corner of box number 2, and we get f of 1, 1/2 equals 2 minus 1 squared minus 1/2. So I suppose this is 2 minus 1 minus 1/2. Suppose this is 1/2. Height number 3, we can plug in the upper right corner of box number 3, and we get 1/2, 1, 2 minus 1/2 minus 1. The x-coordinate is squared, so that looks like 3/4 to me. And finally, height number 4, we get by plugging in the upper right corner of box number 4 with coordinates 1, 1. Two minus 1 squared minus 1, which is 0. So that position is located directly on the xy plane, and that rectangle has essentially no height. Okay, so now to find the total estimate for the double integral, let's go ahead and add together all of the volumes of these rectangular solid. They're solid volumes. Solid volumes, I should say. Now each one of these rectangular solids had a base of area 1/4. So we have 1/4 times height number 1, which is 5/4. We have 1/4 times height number 2, which was 1/2. 1/4 times 3/4 and 1/4 times 0. Now you can do the arithmetic and you can add all of this up, and this number is an extremely poor estimate for the value of this double integral of this particular function. And what we will be developing as we go forward are techniques that can be used to actually calculate these double integrals instead of just estimating them. Alright, now for one more example, let's try and determine the sign of the double integral over the region R, where R is -2 to 2 cross 0 to 2. And we're integrating the function x. Now let's just establish what this region R looks like in the xy plane. This is saying to me that this is a rectangle where the x's go from -2 to 2 and the y's go from 0 to 2. So this is a rectangle, this notation. And let's go ahead and let's fill that in. Now there are a few different ways that we can approach this problem to determine the sign of the integral of x dA over this particular region. One technique, for example, would be to estimate its value by using rectangular solids like we did in the previous example. But that method took a little bit of time, and perhaps there is another way to think about it. So let me show you another technique that I can use to think about problems like this sometimes, which involves using technology to get the graph of the function. Okay, so here we are on GeoGebra, and here we have graphed the function f of xy is equal to just the x value. The y value doesn't have any effect on the output of this function. So graphed in 2 dimensions on the xy plane with the output z acting as the third dimension, here is the graph of our function. Now here in cyan is the graph of the x-axis, and here is the graph of the y-axis in pink here. And the region that we drew on the previous example in the notes, in this example in the notes, stretches from -2 to 2 in the x direction along the cyan line, and stretches from 0 to 2 in the y direction. So from -2 to 2 in the x direction, and from 0 to 2 in the y direction. Now let's have a look at this graph from -2 to 2. From -2 in the x direction to +2 in the y direction, the graph is completely symmetrical. It's doing exactly the same thing in the negative x direction that it's doing in the positive x direction, except in the negative x direction it's below the xy plane, and in the positive x direction it's above the xy plane. So let's go back to the notes. Let's think about this for a second. F of xy has a symmetry. Its graph on the right half of this region is a mirror image of the graph on the left half. Only one of those regions is below the x-axis and one of those regions is above, except on the opposite side of the xy plane. So in terms of single variable equivalence, this is kind of like when we had an odd function, odd f of x, and the net area on the right hand side of the function was a complete cancellation to the area on the left hand side of the function. Cancel. Due to symmetry. What we're seeing here is the two-dimensional equivalent to that. Our function sees symmetrical behavior on the left and the right hand side of the region of integration that we're considering, which means that the positive volume that we pick up from one half of the region is canceled out by the negative volume that we pick up from the other half of the region. So because of that symmetry, we can conclude that the sign of this double integral is 0. Because the left half of r canceled, I should say the integral on the left half of r canceled the integral on the right half of the region r, just as in calculus 2.